But what happened was that during the debate, I wasn't there, but it was reported to me. One of the legislators said, "What do you need special teachers? All you do is add, subtract, multiply, and divide numbers." Now that's the usual perception all around society about what elementary school mathematics is all about. And unfortunately, this perception persists in universities, particularly in schools of education. It's allowed to languish in this state of neglect, namely, well, all you do is multiply, add, subtract, multiply, divide. That's all. You don't need to do anything about it. And it's only quite recently that, as a result of various factors, low performing, the low scores in the international assessment and so on, that it slowly became to light that, well, elementary mathematics may be elementary, but not that easy. And so, if they try to do if colleges try to do a good job to teach its pre-service teachers, it hasn't done that yet. Because there are methods courses and so on, there are math courses for teachers, for elementary teachers and so on. But what you get there is a regurgitation or recycling of the kind of mathematics you get in textbooks. And before the day ends, and you get a doctor and camera or do it, but at least I've way to refer to. In the book in front of you, I make an effort to quote some examples from textbooks about how they want concepts and skills to be taught. And we're going to have a go at that. I say something that might provoke you, but I hope by the end of the 3 weeks, you will come to an agreement with what I'm going to say. At the moment, what is taught in the school is basically what is in the textbooks. I explain this very easily. How many of you, oh yeah, maybe I should do another take on that. Okay. I'm really, this time, I never had this luxury to find out how you think, so I would like to use this opportunity. This is a new thought. I think the math and the textbooks is good. And this is not good. That is so sad. Usual. So 1, 2, 3. I like to have your perception.
Anytime.
What, you all clicked already? 20?
I think that's everybody.
Okay. How many people have checked? Oh, okay, so you see 52% think that are good and 43% are so usable. We used to have a primitive way of doing things. We gave out cards 1, 2, 3, and then we supposed to drop it into a box and then we count them. This is anytime you get more, tell me to use it. So I think, so at least half of you are more or less agree with me. The textbook, the mathematics textbook, is severely defective, and you have occasion to find out what's going on. And so somehow you learn as a student from the textbook, because that's what teachers give you. And the first experiment already show you that most of you realize that you don't learn very much from your college. Therefore, when you go back to teach, what do you fall back on? Fall back on what you learn as a student. And therefore, that body of knowledge inside the textbooks gets recycled from generation to generation. And it creates a culture. And that culture is very serious. I mean, it's really obstructing progress in a way that perhaps you don't realize, and I didn't realize until quite recently. So the first thing I want to say is that and I'll come back to that later. But the first thing I want to say is that what we set out to do is basically rewrite the textbooks, but from a point of view that you're not children. Textbooks are written for children. Right? You're not children, so we don't have to write, but lots of color pictures and things like that. You just write it, say it, from adult to adult, but you can look through it. I hope look through the titles of the title of chapter heading. It's exactly what you're texting. Base value, addition, subtraction, multiplication, division, for whole number, and then fraction, addition, subtraction, is exactly a textbook. That's what we try to do. This is a rewriting of the kind of textbook that you should have, but didn't. So we're going through familiar ground. There's no question about it. What we try to do is to break the stranglehold of textbooks on what's going on in the school. Right? So at least you know what we're trying to do. Now, there are certain things that you may not be used to. Oh, the first thing, above and beyond everything else. I usually do a lot of certainizing just because certain things are never said and I need to say them. But now I put them in black and white, so I don't need to repeat myself, or at least not most of the time. Please go home and tonight read the two things in the front of the book. One is the preface. It gives you a little bit of genesis of the origin of this book and how the motivation for writing it. And the other is directly addressed to you, called to the reader. That's a long, 10 pages, describing how you might read this book, how you might approach this book with profit. Alright, so this sort of general guideline about what we want to do. So you can do that at home, but right now, overall, I want to say a few things, not too much, which is that when you're here, I want you to do things that you probably normally don't do when you teach. But I hope you will do after the institute, or start doing it, and slowly you get better and better. What you said instead of just saying, here's a fact, I'm going to teach you. You think a little bit from the point of view of the learner, the little kids. You can't just make them learn something. You have to sweeten the deal, right? Now, everybody knows that. The way textbooks and the way normally what is done in schools of education is to say we can sweeten the deal by adding in color pictures, by adding manipulatives, by adding more stories, and so on. If you have time, please do all those things. But not when you have not addressed the main issue, which is that you're introducing a mathematical concept, you're introducing a mathematical skill. Those things don't come from God, you know. They come from human beings. So what did human beings think about those things? There's a reason. You have to address that. Above it, forget about all the others. Yeah, the others you have time, this is sort of the dessert. You have money, you can buy dessert. But if you don't have money, at least do the entrees properly. And so what we try to do here is to address the function, meaning let's understand the mathematics. And that's what we try to do. Now, when you say understand something, look, when you try to, look, if you have a friend, the friend comes to give you a sad story of his or her life, well, you have the bare outline from him, but of course you like to know more, like, wait a minute, how did you get into this jam? What did that guy do to you that gave you such a black eye? What do you want to go from here now? I mean, tomorrow are you going to get a job? All these things, normally you just, don't you do those things? Right? If you're in that situation, you want to find out about it, you say, what happened in the past? What's going to happen in the future? I don't think this disagree with you. So when the little kitty approaches a mathematical topic, but you put yourself in their position. Don't you think they want to know? You say, let's add, hold on, something that simple. Right? You say, line them up and do the columns, and there is the answer. Now, all right, do 50 of those while you're here. Now that's not the way you want to be treated, is it? You better say, well, look, you know how to add numbers? Well, you better make sure you know how to add numbers. And next thing is that, you do it, see if we can do it. You give them the big numbers, they have a hard time. They make a mistake, right? Then you say, well, look, there's a shortcut, I'm going to teach you that. Now, if they have made a mistake, then there is much better frame of mind to try to learn something that would lessen the load, right? Then after they say, well, look, what are you trying to learn? They want to know what. You spend effort, is there any payoff? If there's no payoff, why you bother? Well, that's, nothing could be more commonsensical than what I just said. Do you find textbooks that address those issues? In your experience? In any, no, never mind textbook. Do you find any books written for teachers that address those issues? To my knowledge, none. Until recently, at least. So that's what we try to do. Approach a mathematical topic the same way you approach, what's the most popular show now? Oh, I approach Glee. That's a very 2 days ago. Alright, so I mean, whatever the popular show is, you approach it the same way. You just say, well, that's something I'm supposed to do. Then I find out more about it. That's what you want to do. Because every kid will have exactly the same line of thought when they approach any topic. And you try to, but you cannot try to understand what they are thinking, and you cannot relieve their concerns unless you have the answers yourself. And that's what we try to do. Provide you enough background about every one of these topics. How it came about, what's good for, what you have to learn from it, so that kind of thing. Right? So let's get to work right away. Oh, by the way, they know they come in 10 minutes. Yeah, but okay. Now, the foundation of everything about whole numbers, and in some sense, since whole numbers supports everything in mathematics, so the foundation of mathematics. But don't overplay that card, right? But at least for whole numbers, the most fundamental concept is place value. Now, this is people don't realize this is a peculiar topic, peculiar to the way we write numbers. This is not foundational in mathematics. Whether or not there's place value, there are lots of numeral systems in the past. They had no place value in mathematics. Serious mathematics has gone on for 4,000 years. As far back as 1800 BC, people knew the Pythagorean theorem. People knew how to produce the Pythagorean triple, meaning 3, 4, 5. 3 squared plus 4 squared equals 5 squared. 12, 13, 5, right? 4 squared plus 5 squared equals 13. Squared is what? There's an infinite number of those. 4,000 years ago, Babylonians, Iraqis to you, knew how to do it, and would. You can produce any of those things, say it and bring it to it. So, Babylonians had a numeral system that basically had no place value. Yeah, very weird system. We don't have time to go. So I'll give you at least one numeral system. Well, we'll talk about the one that we all know, I think, a little bit, the Roman numerals. But if you're curious, you really have a popular demand maybe in one of the Saturday sessions that we're going to have. I'll give you some other numeral systems, the many of them. They could do mathematics perfectly well. They have no place value. So what? But the advantage of our numeral system is that place value, therefore we can do certain computations. So we should get that straight. What that is. Okay, so now when we do another quick one. Yeah. So that's place value, right? How do you approach place value? So place value. How do you teach place value? So you find good Emeritus. Find good pedagogical technique. We'll have to memorize it. Find some other methods. So how do you, well, even if you have not taught, some of you are not elementary school, of course. But you can imagine, you know what place value is, and say, suppose I teach it, what do I do? Right? So 1, 2, 3. Are they good? Are they inclusive enough? Yeah. Yeah, imagine you know what place value is. Yeah. So how do you think you're going to teach it? Just make a guess.
I can actually put a number to a face if I have.
Oh, it's 41.
How are we doing, Harriet? Do you hear me? Do you hear me? Oh, you do?
I think so. We'll see it.
Can you all see it more or less? So you get an idea. This is number 1. It's quite good. Manipulative. Find some other technique and some others. So by the way, what other? You don't mind if you just discuss it. Some other method. What you're thinking of? In fact, give me an example. I mean, I just want to know how it's done.
An example of a non-base 10 number system.
Non-base 10. And how would you emphasize the place value?
Showing how different numbers are represented in different formats.
I see. So what number system would you use?
I use Mayan math, which is very small, like 20 bits, but just to see that, or the Egyptian math.
Oh, the Mayan, they have place value. It's a base 20, but it's place value.
Yeah, but how it's different than a base 10.
I see. That's a different kind of place, different representation. Okay. Some other choices? No, this 20%, right? 29%. So some other, you must have some other ideas how to do it. What are the other ideas? You want to speak up? You're protected by the picture. What?
The first day.
Right. We do it the second day.
Yeah.
So now that's we're going to approach it. So I'm going to write it down. Right? This is pretty much the main motive, the main, what we call leitmotif, the main theme of this institute. Which is that the more you know, the better you can teach. And so, if you have not tried other ways to do place value, to teach place value, it could only be because no one has ever bothered to tell you that place value in value is not something decreed by some power on high, but it's something intrinsic to the numeral system we have. And so we're going to explain how the origin of place value. All right. The most basic need of human beings in mathematics, you can say the origin of mathematics, is counting. Can anyone see why counting is so important? I'll give an example. Yeah?
I'm a kindergarten teacher, so I have some insight into counting.
Good.
And then I teach at a low-income school, so a lot of children can't count. And it's made me stop and think, what is it to count? What is it? Is it
Very good.
to quantify, to be rote? It's hard and it's difficult to teach children to count that haven't had the experience. So that for me is a challenge. And one of my kindergarten colleagues said when I came to this institute, she hoped I came back with, how do I teach children to count and understand what counting is to a 4.5 or a 5-year-old?
Right. Now, you little kids, you can see. Well, but I want to ask you a slightly different question. You see the problem. I mean, you see the basic nature of counting, right? If you don't know how to count, which I think most of you have never thought about it. Basically, you cannot do anything about whole numbers. You cannot do the arithmetic of whole numbers in any way that really makes sense. Now, of course, you're going to disagree with, but let's go on and then we'll discuss. We'll keep this debate going, right? But think about historically. Why is this at the origin of human civilization? Why would such a concept be so foundational? Again, use your imagination. No? Way back, we have now no clothes to wear, nothing to eat. You still want to count. Why is it?
You want to be fair. You want to know who gets more, who gets less.
Oh, I think
You
it's
want
much
to
more basic than that.
quantify everything.
That would be sort of when the sort of got families and this kind, right? Yeah.
Is it keeping track of your young?
Well, in those days, yes, I guess they had lots. By the way, you know why they had to have a lot of children in those days?
To
Do
survive.
you know why?
They
Well,
survive.
be more specific. To survive, why is it necessary?
To work.
What?
During society, it was to work for you.
Wait a minute. Now, at the origin of human civilization, at the dawn of human civilization, there's no work.
Hunting and gathering.
Yes. You want to
There's more people to
survive.
be able to get food.
Of course, I'm guessing as much as you are, but I would guess that you want to produce as
Survival.
many children as possible because probably over 80-90% of them got killed.
Die, right.
Right? Die of malnutrition, infection, lions.
Right.
Sorry, but that's
Yeah.
right.
Other
That's one of them. So big growth, and then you have to keep track. Well, actually, it's much more than that. Even the origin of human civilization, there are several things that are basic. One is you fight. compete for food, right? You can fight. When you fight, you have an army. Army is going to be more than 5, 10 people. It will be large group. You want to say, how many men are at my disposal? You want to count. Or you're slightly more advanced in civilization, you begin to have cattle or sheep or whatever. You want to know. So in the morning, 59 went out. How come only 57 came back? Something happened. You have to count. Counting is the most basic human function. In mathematics, that is, in mathematically, that's most basic. And once you know how to count, then you do the rest. And that's what we're going to do. So we're going back to the origin of mathematics and say, before you want to talk about adding, subtracting, all that. Talk about the most basic things first. Because those, what we're going to talk about in counting, motivates everything that is the problem. So we want to count. Now, what's the most simplistic way to count, you know? What's the simplest?
Fingers?
Yes. Now, I'll show you how Chinese used to count. Right? 1, 2, 3, yeah, 4. Now we got to 5. Everybody seems to wake up at 5 and say, can't go on like this. Now, so what? Don't laugh. We're Roman, right? Roman numeral. We're going to use Roman. I hope you all know Roman numerals, or you will by the end of the day. 2. See the parallel? 3. Now I cannot vouch for whether the Romans did this. I cannot vouch for that. But it's clear. They had the same misgivings as the Chinese have. This is sit there and see, because you can imagine that, right? What is it, 13 or 15? What? How do you know?
Yeah.
Right? So they just had second thought and say, well, okay. So they might even have had that, and then they say, well, 5 have to do better. When they have 5, then they began to have fancy ideas and said, well, I got 5 here. I simplify this by doing this, right? Now they have Roman numerals have a slight restrictive base value. Something on the left will take away. So 5 away 1 is 4. The Chinese just did it completely different. They say that's too much work. That's all. 5 and now, the simplest way to count is basically you just improvise as you go along. Now, this is pretty much improvisation because like this. Let me do Roman, right? So the next one, they say, once they got wiser, you think they would get wiser and wiser and wiser and get wisest, right? But no, they got to that plateau, they couldn't seem to do better than that, and so they repeat the same silly thing again. And then it came to 9, they said, wow, that's not very good, right? And well, technically they do this, right? But that's not good. So then I guess they use the method of. Okay. Now I'm not going to repeat, and then after that is 11, right? The whole idea is that the simplest way to count is to make up things as you go along. So the Romans pretty much did that. We got 10, and then same thing, 20, 30, 40, 50. Now you know, we got, again, there's something, I get it is the hand. When you come to 5, you go to think 5. So we got 50, they said no. Right? So 50 should not be, 50 would be this. That's so much. So you know what they do for 50?
C, L, D, L.
Yeah.
C times century. That's it.
D is 500.
Right? So usually you repeat, then you come to 100, they say C. 200, 300, 400, then come to 500, then they have another.
D.
And then 1,000. Right? Now, Roman numerals is basically decimal, or this decimal. You know, it's not a special 10, see? Where, right? And 100,000, right? Now, you think the Roman army was big? Could be that big because you know why it could be that big. After 1,000, what is the next thing? The northern numeral. Now, they probably weren't too busy counting because they would have invented 10,000, right? They did. So at some point, they invented some ad hoc rules about putting a bar on top. They suppose 1,000, million. And then they start saying, put a bar where everything is 1,000-fold of the original value. So I think, but don't bet on this. So this would be 10,000, and so on. So, but that's beside the point. The point, which is completely reliable, is that you can see the most natural impulse, which is that if I want to count, I just make things up as I go along. So if the Romans had started to do any serious astronomy, which they didn't, they would say some distance is big, 1,000 is not good enough, they would have invented 100,000, 10,000. There was some other crazy symbol, right? What's wrong with this? What's wrong with this? Right? Let's consider 2 times 3, right? Now you learn this, that there's nothing to learn, right? 13 times 30 is what? Do 6 and then just 2. Or 2 times 300 is what? 6. So it's basically, basically, in our numeral system, this is the basic. After that, see? Right? Nothing more to learn. Right? Let the new Roman numeral. 2, or this, oops, oh God. So this corresponds to 2 times 3 is equal to 6. 20 times 3 is what? 1. 30. It's 600. So 600. You think it's the same thing? Of course not. Right? It's 500. What's this? 2 times what? This is what? It's also. So let's make things more interesting. Figure out another. I just want to show you how things go wrong, right? So, mil. As I told you, I don't know of any 5,000 in Roman numerals. So what do you think I'm going to do?
Wow.
Now, take a look. What conclusion do you draw?
No pattern? Not, this one is a pattern and that one doesn't.
Yes, but maybe you might want to rephrase that a little bit as saying, on the left, how much do you have to learn? Basically what? 2 times 3, 6.
3.
On the right side, what do you have to learn? It's what you have, that's what you have to learn. Next time your kids buy things, how many of you are real elementary teachers? Okay, how much complaint you have from children that they don't want to memorize the multiplication table? Often, little bit, not. I tell you what, see, that's why knowing something gives you many more options. Right? Next time someone complains about, I don't want to learn anything that, you'll threaten them with, all right, don't learn that. Learn the multiplication table for Roman numerals. You can imagine the rest, yeah? Yeah. 2 times 12 would be unimaginable. 2 times 13 is something else. Try that. So you can get the idea that the reason we have our numerals is that it causes, it leads to computational simplicity, or as we say, symbolic simplicity. But it's at a cost, and we'll talk about that in a minute. So what is our Roman numeral? Okay, so you see this. So what would you characterize as the key features of the numeral system we have? So let me give you the name. This Romans, our numeral system, as you know, is decimal because on base 10, right? 1, 0, 1, 0, 0. But the official name is Indo-Arabic numeral system. For good reason, well, for good and bad reason. The good part of it is that it was first, basically the wiggles, not quite the same, but essentially the same wiggle, what meaning is. These wiggles, I call them wiggly, right? Not quite like that, but essentially they were carried over by the Indians to the Arabic Empire, Islamic Empire, about 8th century, about 750. So the Hindu scholars came to visit. Well, the Islam Empire was very learning oriented. By the way, you know where the Islam Empire was seated in those days?
When? They're using when or where?
Where was the empire seated? Baghdad. Baghdad. Yeah. So you should know. This is another example of knowing something, don't know something, little bit, know enough of it to know the whole story. But that was a seed of human civilization in the Middle Ages. Without that, there would be no Western civilization. So they were a great center of learning, and so they summoned all great scholars from all over the place, and the Hindus were summoned, and they brought along this. So the Arabs seized on it. They had a small fight over. They had their own numeral system, but then once they saw that, they understood the superiority. They took over, and then, of course, overcome some resistance. And then in the 12th century, 11th century, Europe had no civilization back then. So the Arabs, the most of the conquered Europe, which you all know, go to Spain. Anyone been in Spain? Portugal? You saw the vestige of the Islamic civilization?
Yeah.
That was I think the last stronghold of the Arabs was in the southern part of Spain, I think. Then they were driven out. So they conquered most of Europe, a lot of Europe, not most, along the Mediterranean coast. So they carried that bit of civilization to Europe, and it was the Europeans who recognized the great superiority of that system. But they had to fight 4 centuries to get it done. And by 1600, the Hindu-Arabic numerals, as we know it, became universal. And then after that, in Europe, and after that, it was, by now it's universal. Now, it's universal in the sense, as I told you, this is correct, because that's historically what happened. Now, people got the wrong impression that was the first and only decimal numeral system like that. And that's wrong. The Chinese have had it for about 2,500 years at least. Within history, the record doesn't go that far back, but it's quite certain that by first Berkeley, it went at least 28th century. Entirely the same, completely, except for one thing. We didn't have those wiggles. So I give you the whole numeral system. You can see why we did that. I give you the 4 of them, right? Oh, let's see. No, yeah, 0. Sorry. Sorry. That's 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you see that it's really a local composition, right? You can't write like that. So the Chinese adopted the numeral. When Western civilization was introduced in China around 1700. Around that time. But the Chinese numerals, while the Chinese did not just have those numerals, they had negative numbers, they had fractions all the way, or at least in the historical record, we had fractions and negative numbers around 2nd century after Christ, 200 AD. So much more advanced. So these are the facts. But of course, no one knew much about it. Because of linguistic issues, people didn't understand the Chinese numeral system until recently when people started to write about it. And much worse than that, historians didn't understand that way back, but if you look at history, textbooks on the history of mathematics, I think as of 10 years ago, most of the books, when they talk about Chinese numerals, they got it completely wrong. They didn't even realize that the numeral system, as we know it today, was completely in place in China, and they started to talk about incomprehensible. Yeah, so language barrier was very great.
What's 10?
I'm sorry?
10.
Oh yeah.
Thank you.
Okay. All right. So you tell me. Well, this is all right. I'm erasing this. All right? Are you erasing this? So you tell me what's so great about our numeral system. What are the key features of the Indo-Arabic numeral system? Why is it important?
So you don't have to keep on making up symbols.
Okay. Go a little further. And make it more compact. In other words, pin it down a little bit more. Keep going. You can do a little bit better. 10 symbols.
And it's infinite?
No. We use only 10 symbols.
Yeah.
That's the key feature. Right? With the Roman numerals, you don't know how many symbols there are because so long as you're counting, you're going to make up new symbols. Right? So, 10 symbols. Right? Yes?
Well, I think part of it is what it says in the name of it. It depends on place.
Yes. So that's the trick. The two facts together make up our numeral system. One, okay, I write that. What? These are the things you can teach your children. Here are the two characteristics. Use only 10 symbols. Right? And rely on the position or place of the symbols to represent any number. Wow. No matter how large. These are the things that give rise to place value. So let's be a little bit more precise. So we'll come back to the main theme. As I said, the origin of everything is counting. Right? So with only 10 symbols, how much can you count? You write it out. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you're Roman, you go on and you say, another one, X. Right? But rule number 1 says you don't. And by the way, so you know why you don't, right? Because I just showed you. No Roman numerals, you make a new symbol as you go along, there's so many things to remember. You don't. So you say, no, I do self-control. So now you insist on counting, no? There's a cheap way to do it. Namely, you want to keep counting? Repeat yourself. No? Not? No. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you have 20. But not enough? Well, keep going. Not enough? I keep going. And so on. Now I don't want to overdo it, right? And so on. That guarantees that you can keep counting. 1, 2, 3, 9. 1, 2, 3, 4, 5, 6, 7, 9. You're going further. The only thing wrong with that is not very clear. What is the difference between 13 and 3? So of course, the way you do it is you will traverse this, right? And you traverse it again. And you traverse it again. You can go on further. That guarantees the possibility of continued counting. Right? The only problem with that is, so now, if you're going to teach this, you have to be very careful. There's an ambiguity. Count, what do you mean by counting? So that could, I'll show you in specific examples that they're going to be very bad. So we're going to be very specific about what we mean by counting. When I say we count, when we count in steps. First step, we start with 0. Second step, third step. That's what we mean by counting. Okay? I'll show you why this is necessary. So be very explicit. When you count, you say you start. We're going to start with 5, of course. Doesn't matter. But you start counting somewhere, you look at the number of steps you get to land and the place. Right? So this is the second step. So the second one. You start at 0. Okay? Right? So you do that in a second. You count 3 times, and then you do 3 steps, you end up with 3, right? Now you count 13 steps. What do you get? There's 9 steps, right? 10 steps, 11, 12, 13. So you count 3 steps, and you count 13 steps. You end up having the same symbol. That's not tolerable. The thing that's wrong is that all the rows are identical. You want to differentiate among all these rows. How can you do that? I repeat, right? Right now you don't. You just say continue counting by repeating the rows. Yes, you can continue counting forever, except that you're causing yourself into trouble. You say, oh, go to the 3 door, and then go in, and there will be a stick waiting for you, right? Which you mean the 13. That's not good, right? But you still, but how? You know, right? You keep going, and it's still not ending. So the major breakthrough that the Chinese had and the Hindus had was we can differentiate on rules by simply saying what? What row is it? Right? So you say this is the 0 point. You start with 0, right? So by the way, what I'm telling you is historically slightly inaccurate. 0 came much later. But you don't worry about that. So this is 0 row, so therefore you say this is 0, 0. This,
But that's the nothing row. That's the 0 row.
yes, that's nothing row. Because you start with 0, so you have to be consistent, right? That is it. And the next row, well, you just use it. In other words, you count because you talk about counting, right? So this, the second row is 1, 1, 1, 1, 1. Third row, then you put something in front. I'm going to help to pay a minute. Oh, sorry. Right? And so on. Look at that. Right? Now, first thing, you do it this way, you have increased your ability to count by tenfold, right? What's the bigger number you can count? 99, right? You have added a number in front of the rows to indicate that you're counting how far down you go. Now that's the origin of place value. Place value is not something you create by God. It's something you decide what you want to do, and you do it. And it's very solid mathematical reason. You do it because whatever you're going to do, you're stuck with 9 symbols, therefore you make do with what you have got. So at this point, now you want to explain to children. The usual way is to find some fancy method to impress on children that the number 34, the 3 is 30, the 4 is 4. Just how to drill it into their head, right? They can do better, they can do much better. You tell them, why is this 3 30? Well, because why? This is the 4th row, right? You get to the 4th row after you have traveled how much? How far? 110, 210, 310. This is the 4th and 30th number. See? This is 9th step. Alright? Now let's do it slow. You go along here, 9th step you land here. This is the 10th step. You get to this point after you have traversed 10 steps. Then 10 plus 9 to 19th step, right? 20th step. Right? So this is the 2. The 2 here says it's the 3rd row. The 3rd row means you will have 2 rows behind you. You're done 30 of those numbers. You go another 9, and then 10. That's 30. That's the 30th step. So the 3, which tells you, is the 4th row, the beginning of the 4th row. You have 3 rows of 10s behind you. That's how you play that. That label reminds you what row you are counting. So now, 34, well, that's clear. The 3 is the thing you put in front to indicate which row this number sits in. You're 30 behind it. The 4 is, on this row, how many steps you count to get here? Well, guess what? 1, 2, 3, 4. The 3rd row, 4th number. That's what it says. 34. And same for everything else. Now, you understand this principle. Is there anything that would hold you from going further now? You have exhausted 2 places, 0 to 99, right? Oh, by the way, so let me just a footnote. Nobody writes this, correct? Well, is raised from 0 to the left. That's the reason. Why every number you would put any number of zeros in front makes no difference. You normally erase you don't want to do that. Because you know that indicates that it's the first row. Right? So those are called single digit numbers, meaning that the zero is fake and the read doesn't count. But these are called two digit numbers. You'll use up two positions, right? You still insist on going further, so what do? You repeat exactly the same thing. Now, so what you do is what? You now have 100 numbers from 0 to 99, right? You keep going. Well, what's the main idea? I can keep going by repeating myself. 0 to 99, 0 to 99, 0 to 99, keep going. And then you say, well, I want to distinguish among the rows by putting a label in front to say first row, second row, third row. Same idea here. And then after that, you can do as much as you want. And then that's how you can count forever using only 9 symbols. And the symbolic simplicity, okay, is purchased at the price of cognitive complexity. This is cognitively complex, and this is why giving you kids nightmares sometimes. Why learning this system? Yes, you only learn 10 symbols. Unlike Roman numerals, God knows how many you have to learn. D and C and X and Y and God knows, right? So it's very tight in that sense. But if you can just make things up as you go along, that's always the simplest. Yeah? All the kings and emperors love to do that. We have restricted ourselves to 9 symbols, so you will limit yourself the amount of what you have to do. But in exchange, of course, then you'll have to work harder to make sense of the limited resources. That's always the price. And that's all of arithmetic is basically to unravel the inherent cognitive complexity of this symbolically simple system. And that's what we're going to stand for this on this. Now, instead of me going on, I don't want to go on to 3 places, 4 places. I want to make sure you understand this concept. So I don't want to do this. Suppose instead of 9 symbols, I don't give you 9 symbols. I want to give you 3 symbols. Wait, hold a second. Let me see what did I decide to do. It's the decision I wanted to make. So 3. No, 4. 4. We need to 4 symbols. Okay. Suppose, so we have 9 symbols to play with, right? What if I give you only 4 symbols to play with? Same principle. Can we count forever? Okay, so let's do it.
0, 1.
Right? So you start by saying 0, of course. 1, 2, 3. Right. To continue, well, the first thing is I just repeat myself. And so on. But then I know that because of repetition, it introduces confusion. Therefore, I differentiate among them. So I would, for the first time, I make it still. Put something in front to indicate this is the 0th row. Something in front says this is the 2nd row. 3rd row is 4, 2, 1. Fourth is well, if you only have 4 symbols, you come to an end. Now, first of all, you understand what's going on. Yes? So, raise the question and I'll explain it. Okay, now, of course. So let's do something slightly illegal. Well, I say you will do 4 symbols, but of course we know our own numeral system. So from the vantage point of our numeral system, let's count. This is going to be confusing. You tell me, right? How many numbers can I count using this numeral system? Does that make sense? See, so I'm allowing ourselves only 4 symbols, 0, 1, 2, 3, right? If I only use 2 places, how far can I go? If I count?
39.
No. That's all you've got. How many numbers are there?
36. So 90.
16 numbers.
39.
Well,
Are you counting on a number line? Counting the spaces?
no. Let's try again. 50. I'm giving you only 4 symbols, right? And if I only give you 2 places, how far can you count? You start at what?
0.
Well, depends what, so we have to be careful about. This is the reason for saying, when I say how you count, you have to be careful. You either say 15 or 16, right? But in our normal sense of counting 1, 2, 3, 4, you only get to what? This is number 15, no? Because, right? You want to count? You start with this is the first number. So it's on 0 now, so to speak, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Right.
So if I only use 2 places and 4 symbols, I'm stuck when I get to the 15th number. In other words, if you have 15, suppose you have 20 donuts in front of me and I want to count how many there are, and then 33, then it starts at the 15th donut. Then I cannot go to the next donut because I haven't got any numbers. But you know there's a quick way to see why there are only 15 numbers here. Because you have 2 places, right? You can think of it as 2 boxes. In each box you can put in a number, right? How many numbers can you put in here? 0, 1, 2, 3. 4 numbers. How many numbers can you put in here? 4. So 4 times 4 is 16. The 16 numbers you can write down, but when you count, you ignore the 0, 0. And that's why. Good? So let me repeat. So let me make sure everybody follows. If you are restricted to 4 symbols, and you're only using 2 places, then how far can you count? Well, you only can count to, with reference to our own numeral system, you start after the 15th object. This 15th. We good? Now, there's a reason why I'm using 4 symbols. At this point, you want to go further, right? You want to go further, what do you do? Repeat the same thing, right?
Yeah.
So you say, well, I'm going to write the whole thing in one row and then repeat the whole rows, right? So let's start writing it down first. So as usual, we just ignore the 0 in front. Right? So just write 0, 1, 2, 3, right? And then 1, 0, right? 1, 1, 1, 2, and so on. Up to 3, 2, 3, 3. I have listed all the 2-digit numbers of the 2 digits here. So you follow me up to this point. Right? Now I want to play the same game, of course. Then I say, well, I can keep counting. If I don't care about repetition, then and so on.
But then you have confusion.
Exactly.
Yeah, because then your 1, 1 is going to be the same as the 1, 1 in the
Yes.
row.
Now, actually, I did something very, very dumb. Why did I do that? I took away the 0, which is, you see why this is very dumb. I should put it back. Do you see why?
Oh, okay.
Because I'm going to add something in front, right? So we respect the fact that we have 2 digits. So I have 4 rows, or you go on forever, but it doesn't help. So I want to distinguish among the rows. Therefore, what I have to do is to label the rows differently. We do exactly the same thing by what? The first row is 0 in front, right? Now you get the second row, you get a 1 in front. Third row, you put a 2 in front. Fourth row is 3 in front. That's how you get the 3 digits. If you have only 4 symbols. Now, of course, we do the things like that. We always try to relate to our normal way of doing things, right? Right? So let's see. In this numeral system, with only 4 symbols, what would be the 32nd number? Which is the 32nd number? Well, how many are there in one row? 16 numbers, but you get it. Are they, sorry, are they?
They're coming up. Go
Okay.
ahead, I told them to interrupt when you're.
Yeah. Good. Okay. So we're gonna. Somebody's gonna come. This MSRI, Mathematics Research Institute, and Berkeley Sciences. And some higher up is going to come up. So welcome to make you feel welcome. So after that, we're going to disband and then come back to continue this. Okay?